So if you look at the calendar, this will probably take us about a day and a half to cover, hopefully just a tad less than that. Then we'll do 4.5. 4.5 also takes about a day and a half. So today is going to be all 4.4. Tomorrow will be a mix of 4.4 and 4.5. And then we'll finish up 4.5 on Wednesday. This section is on something called L'Hôpital's rule. If you were listening to Juan's conversation beforehand, he took a bunch of French. It's not La Hospital. You pronounce this L'Hôpital. People will look at you funny if you say La Hospital, although there's some mnemonic devices you can use to help remember how this rule works. But it's on L'Hôpital's rule, indeterminate form. And if we have time, I'd like to go over something called relative rates of growth, because they're not in this textbook, but they're a very typical usage for L'Hôpital's rule. It actually has some nice, interesting applications. So we're going to start off with a pretty darn easy starter question, just 4 little parts, very simple function, but we're going to use this relationship a little bit later on. So we're finding the limit as x approaches 0 from the positive side of the function x. What's the limit? The limit's 0, okay? Well, let's say we're taking the limit as x approaches positive infinity of the reciprocal of x, which is 1 over x. So we're no longer going to 0, we're going toward infinity, but we're no longer using the identity function, we're using the reciprocal of the identity function. What's the limit? The limit is also 0, okay? And similarly, if we're dealing with this one, if we take the limit as x approaches infinity of the identity function x, its limit is infinity. If we change the point of interest, if we're no longer interested in finding the limit as x approaches infinity, but we're interested in finding the limit as x approaches 0 from the positive side, we're keeping all the values positive here, of the reciprocal, what's that limit? That limit is also infinity. So we can match the behavior, okay, the end result of the limit, by changing the function from the identity function, by changing x to 1 over x, and changing the point of interest from 0 to infinity, or vice versa, okay? Now, that might seem like, well, that's kind of silly. Yeah, that kind of makes sense. This actually can make some problems a heck of a lot easier to deal with, because sometimes finding the limit as x goes to infinity is a pain in the butt, okay? But finding the limit as x goes to 0 is not too hard, okay? It has some nice graphing features, because imagine if you were trying to look at a graph and determine what the limit was out toward infinity. Well, how far out do you need to go on the graph? Okay, and do you really want to mess with your calculator and make that do that? So we can trade behavior at infinity for behavior at 0 and vice versa if it comes in handy. Okay, so as we've said many times, and maybe to your annoyance, calculus would not be possible without limits. Now, we spent a whole chapter talking about limits, and everything that we've been doing with derivatives and all of that sort of stuff is based on the idea of a limit. We don't talk about it all the time, but that is in fact what it's based on, okay? And that's how we do those. So we're going to come back and spend some time looking at limits today and part of tomorrow. So let's take a look at example number 1. In order to do these examples, and we've seen some of these before, but we're going to go a little bit more in depth, and then I'm going to show you an alternate way to do these. What we've typically done is we've either tried direct substitution, or we've had some algebraic trick that's made it able for us to do this. So when we're doing a problem like this, again, the first thing we want to do is we want to try and do it by substitution. So if I plug in a 1, I get a 1 here, a 4 here, then I subtract 5, so I end up with a 0 in the numerator, which all by itself isn't a bad thing. But when I try and plug a 1 in the denominator, I end up with a 0 also, okay? So when we ran into this before, we looked at this and we said, okay, well, let's see if we can factor this. So I'm going to take the top and factor it. The bottom's already factored. We're looking for numbers that multiply to be -5 and combine to be +4. So that's going to be x plus 5 and x minus 1. That would do it, wouldn't it? And if I've got the limit as x approaches 1 out front here, I can go ahead and cancel these, because remember, if I were actually interested in what's happening at 1, I'd be canceling a 0 with a 0, okay? And that's not a 1, okay? Or at least not always a 1, okay? But we're not interested in what's happening at 0. We're interested in what's happening around 0. So for anything except for 1, these two are exactly the same number. They're not 0. I can cancel them off. So I end up finding the limit as x approaches 1 of x plus 5. So I end up with an answer of 6. Now, we've done this one several times, and I realize you already know what the answer is, but humor me. We're actually going to go through and do a little bit of a proof on this one. Okay, we've done this a couple of different ways, and now we're actually going to come up with a proof. So if I do this by substitution, I end up with a 0 on the top, and I end up with a 0 on the bottom. Okay, similar to what this one was right here, but the answer to this one is not 6. Okay, and that's what makes these limits that are of the form 0 over 0 kind of interesting. Okay, and that's most of what we're going to spend today talking about. So if I were going to do this problem, here's what we're going to do. I realize we already know that the answer is 1. Okay, we've dealt with this several times. We've looked at a graph. We've looked at some arguments using geometry and the squeeze theorem and stuff like that. But we're actually going to start this one off, and we're actually going to do this one from scratch. So here's how we'd set this up. So let's draw a little coordinate plane here. And I'm going to draw part of the unit circle. Okay, I'm going to draw the unit circle in the first quadrant. Okay, that doesn't look anything like a quarter circle. Okay, and that only looks slightly more like a quarter circle. Okay, so, and then I'm going to draw this line right here. Okay, now it's on the unit circle, so this is a 1. And I'm going to draw this angle right here, and we do this in radians, so that angle right there is x radians. Okay, now I'm going to draw a line straight down, and I'm going to draw, let's see, let me change colors here. I'm going to draw a line that's straight down in blue, and I'm going to draw this line right here that just barely touches right here. Okay, now if it just barely touches at that point, what do we normally call that type of line? Call that a tangent line. Okay, I'm going to draw that tangent line just from right here. And the reason we call this a tangent line, and I'm going to change colors again just to color code this. The reason I call that a tangent line is because it's tangent to the circle, and it meets that radius at a right angle. So that right there is a right angle. Okay? Now we need to remember some geometry in order to do this. Let's see, let me do this in blue. This line right here that comes straight from this point straight down. Can anybody tell me how long it is? No, because it's not 45 degrees. The angle right here is x. It would be the y-coordinate, wouldn't it? It would be the y-coordinate on the unit circle. And the y-coordinate on the unit circle is the sine of the angle, isn't it? Well, the angle is x, so this one right here is the sine of x. With me there? Okay. All right, let's do this one right here. Yeah. Sine of x is the blue line. Yep. So if this is a right angle right there, this would be the y-coordinate on the unit circle, so it's going to be the sine of whatever that central angle is that right there, that reference angle. Okay. No, I'm gonna line these up. Okay. Now, if you have an arc on a circle, if you want the arc length, does anybody remember the formula for arc length? S equals r theta. Okay. Now, what's the radius on this circle? 1. What's the central angle? X. So how long is this black curve right here? It's x. All right? Okay. And how about this little red line right here? How about from here over to here, knowing that this is a right angle right there? So let me draw this kind of like this. I'm going to put the right angle right there. This is a 1, and this right here is an x. Any ideas on how we'd get this right here? Yeah. The tangent of x would equal the opposite, which is a question mark over 1. So that opposite side, that question mark, is the tangent of x. Okay? So this right here is the tangent of x. Any questions there? Okay, that's the geometry of it, and from here on out, I'm hoping this is relatively easy, assuming I can remember how these things relate. So let's think about this for just a second. Okay, if I were to put the blue line, the black curve, and the red line in order from the shortest to the longest, which of those three is the shortest? The blue one, isn't it? Because that goes straight down. Okay, the quickest way to get to this horizontal line here, to get to the x-axis, is to go from this point straight down there. Okay, so the smallest one is the sine of x. What's the next shortest of those three lengths? The curve, right? The x. Okay, so I'm going to say that that one is greater than or equal to the sine of x. And then this one's definitely the longest. I mean, this would be a silly way to get to the x-axis if you wanted to get there as quickly as possible. Going in a straight line directly there to meet it perpendicularly would be the shortest route. A curved route that's pretty close to where we'd hit this point would be not too bad. But to head off in this direction, that's going to be quite a bit longer. So that's going to be greater than or equal to the tangent of x. Okay? Now, does everybody understand the geometry? Okay, and I have this little inequality set up here. Sine of x is smaller than x, and that's smaller than tangent of x. Okay, and depending on how large this angle is, we're leaving open the possibility that if I were to close this off completely and make x equal to 0, they'd all be exactly the same length, because they'd all be right on the x-axis. Everybody with me there? Okay, so here's what we're going to do. We're going to take this, and I'm going to rewrite this as a sine over a cosine. So I'm going to write the sine of x. Let this catch up here. Sine of x less than or equal to x, less than or equal to sine of x over the cosine of x. Now, if I were to take something like, well, let's see. I'm trying to get this. I need a sine x over an x. What if I went through and did this? Okay, now I'm assuming for the sake of this argument that I'm in the first quadrant, so the sign is always positive. Could I go through here and could I divide by the sine of x in every one of these? And I'll multiply this by 1 over sine of x. Would that be okay as long as I'm multiplying by a positive or dividing by a positive? Change the direction of the inequality? Nope. So here's what I get. I get 1 less than or equal to x over the sine of x. Less than or equal to, well, this is just going to be 1 over the cosine of x. And we're going to resist the temptation to think of that as a secant, because that's not going to be helpful here. And I'll show you why in just a second. Okay? Any questions? Okay. So let me show you this inequality, and I'm going to ask you if this is true. Is this a true statement? 1/3 less than or equal to 3/4. Is that true? Zach? Yeah, it is. Okay. Less than or equal to. Less than or equal to. 1/3 is less than 3/4. Okay. That is a true statement. Okay. What happens if I take this and I flip it over? What if I flip this one over and I flip that one over? What do I need to do with the inequality? Okay. Change the direction. Because this is now 3. And this is 4/3. Okay, they're both greater than 1, but this is a lot bigger than 1, so I have to switch the direction of the inequality. So again, the goal here is to get sine of x on top and x on the bottom. Right now I've got it inverted, so I'm going to take every one of these and I'm going to flip it over. Well, the good news here is if I flip 1 over, I get a 1. If I flip 1 over cosine over, I get cosine, both of which I'm a little more comfortable working with. Are you? And then what I have right here is sine of x over x. Okay. Now, whoops. What do I need to do here? Switch the direction. Okay. Now, we could leave it like this and finish this off, but what we'd normally do is this. We normally write them in ascending order. So I'm going to write cosine of x less than or equal to sine of x over x less than or equal to 1. Okay, now, does that look familiar at all? Anybody remember this? The hint there was use some geometry in the Squeeze Theorem. If I know that this is always in between the cosine of x and 1, couldn't I just do this? Let's come back here and let's put a limit as x approaches 0 in front of every one of these. And what is the limit as x approaches 0 on cosine x? 1. You can do that by substitution. Okay? Cosine of 0 is 1. So I get a 1 here. I've got a less than or equal. I've got a less than or equal here. There's not even a variable here, so that's a 1. So we've got that the limit as x approaches 0 of sine of x over x is equal to, well, it's somewhere in between 1 and 1. So what's the answer got to be? Got to be 1. So we've just gone through, this is the most comprehensive proof that we've gone through so far, that this limit is indeed 1. Okay? Now, that took about 10 minutes to go over that fact. Okay, we're certainly not going to spend that much time on the rest of them. But here's what's interesting about this. On this one, this was a relatively easy problem right here. The limit, if we tried to evaluate it by direct substitution, was 0 over 0. Do a little bit of algebra, and we find out that the limit is actually 6. It does exist. It's the finite number 6. On this one, by direct substitution, we end up with 0 over 0. And through a whole bunch of manipulation, we find out that the limit is actually 0. So they started off looking the same, but they got completely different answers, and the same is true on this problem right here. Again, using a different technique that we've used before. So let's take a look at this one. Again, by substitution, this would be a 1 minus a 1. So this is going to be a 0 on top and 0 on the bottom. So the technique we used for this is it was kind of like rationalized. We multiplied by the conjugate of the numerator. So here's what we end up with. If I take the cosine of 1 minus, or cosine of x minus 1 over x, and I multiply by its conjugate, so that's the cosine of x plus 1 and cosine of x plus 1. Then what I end up with is, let's see, if I distribute that through, I'm going to end up with the cosine squared of x minus 1 over x times cosine x plus 1. And again, we want to resist the temptation to distribute that through. Does anybody remember what we did with this? Okay. We used the Pythagorean identity and either substitute for cosine squared or substitute for cosine squared minus 1. Either way, you're going to end up with this. You end up with negative sine squared x and x is cosine x plus 1. Still can't evaluate it by substitution. If you plug a 0 in the top, you get a 0 here, and you get a 0 in the denominator, so that's not going to work. Ideas? Is there any part of this that looks familiar? Is there any part of this that could be broken up so that it does look familiar? Oh. Okay. So here's what we're going to do. I'm going to write this as the sine of x times the negative sine of x. And then on the bottom, in fact, I'm even going to do this to make it more clear. Why bother writing one single fraction bar when I can put this over x and I can put this one over the cosine of x plus 1? All the same factors are represented, but now I have something that I can figure out. This limit as x approaches 0 is 1. We've already established that. And then I can find the limit as x approaches 0. Well, let's see. What do I get on the top here? Yeah, so I'll just write this down, okay? This is a 0, and this is a 2. So I've got it in a format where I can actually compute the answer. I've got this limit is 1, this limit is 0 over 2. Remember, 0 in the numerator is not a problem. That's just 0, okay? As long as this bottom number is a finite number other than 1, other than 0. So the answer on this one is 0. So let me zoom out and take a look at all three of these. I had 0 over 0 on each one, but the limit here was 6, the limit here was 1, and the limit here was 0. Okay? So it seems a little bit weird that plugging in by direct substitution gets us 0 over 0 in every case, but the answer on every one of these is different. Okay? And that's where we need this L'Hopital's rule. That's why we study this particular type of form. So in each case, the numerator tends to 0. And if the numerator tends to 0, so if the top of a fraction is getting closer and closer to 0, then that would lead us to believe that the limit would also be 0. Because if the top's turning into 0, normally that makes the whole fraction equal to 0, right? Okay? But at the same time, the denominator is tending towards 0. And what usually happens if the denominator tends towards 0? It's getting smaller and smaller and smaller. A lot of times the overall limit turns out to be infinity, right? Because if you've got a number divided by something that's getting smaller and smaller and smaller, the overall quantity gets larger and larger and larger, okay? So the limit tends toward infinity, okay? So the question here is, which of these two wins? We've got these two competing interests. The numerator's driving the answer toward 0. The denominator's driving the answer toward positive infinity. So which one wins? Is it 0? Is it infinity? Or is it somewhere in between? It's a compromise, okay? Well, as we'll see, it's usually a compromise, all right? So whenever we have a limit in this form, 0 over 0, it's called indeterminate form. And the reason we call it indeterminate form is because if it's in that form, it can't be determined what the limit is. At least without some more sophisticated tools like we've been talking about here today. Okay? Factoring, not that bad. Multiplying by the conjugate, not that bad. Okay, but going through and doing some geometric argument to prove that sine x over x is 0, that's kind of a pain. Okay? So, 0 over 0 is the most basic indeterminate form. We run into that a whole bunch. But there are some other ones. The next most common is infinity over infinity. Okay, what's happening there? Infinity times 0, that's an indeterminate form. Infinity minus infinity. Okay, seems like the answer ought to be 0, but it seldom is. 1 raised to the infinity, or something really close to 1 raised to the infinity. 0 to the 0 and infinity to the 0. Okay? And again, when we put those numbers there, we're talking about a quantity that's approaching 0 raised to a quantity that's approaching 0. We're talking about a quantity that's approaching infinity raised to a quantity that's approaching infinity, or sorry, approaching 0 there. Okay? And the tool that we typically use for these is L'Hopital's rule. Okay? So a guy named John Bernoulli discovered it, but a Frenchman named Guillaume L'Hopital, he's the one that published it and made it famous, so that's why we call it L'Hopital. Now, whenever we use L'Hopital, I usually abbreviate it this way. If you use L'Hopital's rule, you kind of want to cite the fact that you're using that rule. It's kind of part of showing your work. So I usually abbreviate it with an LHOP, so call it LHOP, call it LOP, call it whatever you want, okay? Just don't say whatever you want in front of a professor because they might make fun of you, okay? So this is how L'Hopital's rule works, and you've got a copy of it in your notes, and this is directly from the textbook, and this is how this textbook presents L'Hopital's rule. It says, suppose f and g are differentiable functions, and g prime of x is not equal to 0 on an open interval that contains a, so the point of interest is a, and we're making sure the derivative exists everywhere, and the denominator is not equal to 0 around there, okay? And then it says, suppose this. Suppose that the limit as x approaches 0 of f of x is 0, and the limit as x approaches a of g of x is also 0. So they're both going to 0, or they're both going to either plus or minus infinity. It doesn't matter which type of infinity, either positive or negative. Okay? So this is a very long mathy way of saying you've got a form of 0 over 0 or infinity over infinity. Okay? Those two most common indeterminate forms, they're both ratios. They're both fractions. 0 over 0 or infinity over infinity. Okay? If we have that form, then here's how L'Hopital's rule works. If you want to take this limit, you can actually find the limit of the derivatives, and they are exactly the same thing. Now, when we say find the derivatives, it means find the derivative of the top, find the derivative of the bottom, and then find that limit. And usually that limit is easier. Okay? So we're not applying the quotient rule. Please don't do that. We're simply finding the limit of the top and the limit of the bottom. It's even easier, okay, than if you were to find the quotient rule. Okay? So as long as we can find that limit, we're going to get an answer to this. So let's take a look at this next example. We already know what the answer is, but we're going to figure this out using L'Hopital's rule. The first thing we do is we try direct substitution. We show that it's in indeterminate form, and then I cite that I'm using L'Hopital's rule. So L'Hopital's rule tells everybody that what I'm going to do is I'm going to differentiate the top, and I'm going to get the cosine of x. I'm going to differentiate the bottom, and I'm going to get 1, and then I'm going to bring that limit back, and I'm finding the limit as x approaches 0. And on this one, piece of cake, what's the limit? Limit is 1. So there's yet another proof that the limit as x approaches 0 sine x over x is equal to 1. By far the easiest, maybe a little irritating at this point, maybe not, that we did all that work to show that this limit was 1, and yet we can just use L'Hopital's rule, okay?
Well, we just sort of proved L'Hopital, so it wasn't some black chop say, hey, you just do it really good.
That's right. Okay, so let's do this other one. We also did this one a second ago, so here's how we handle this problem. Again, we have to plug this in and make sure that it's in indeterminate form. If you plug a 1 in, you get a 0 on the top, you get a 0 on the bottom. Again, we're going to indicate that we're using L'Hopital's rule, so we'll cite that. And then we find the limit as x approaches 1. Nothing changes about the limit. We just find the derivative of the top completely separate from the bottom. Again, not quotient rule. So this is going to be 2x plus 4 over 1. No problem now with the denominator. Direct substitution will lead us to a 6, just like we got before. Okay, so let's do something that's more interesting, a problem that we haven't done before. And please take time to appreciate how cool this rule is. Okay, think about how much time this saves us. So if I plug in a 0, I get 0 minus 0. So I get a 0 on the top. Plugging in a 0, I get 0 there. So again, I'm going to cite that we're going to use L'Hopital's rule. I'm going to find the limit as x approaches 0. This is a 1. The derivative of negative sine is going to be negative cosine. And the derivative of the bottom is going to be 3x squared. Very good. Okay, so imagine if somebody came in right now, and I'm going to kind of pretend like I'm erasing this right here, and we were staring at that problem right there, and we knew L'Hopital's rule. What would we do next? Well, we'd make sure that it's in indeterminate form. Okay, so we'd show, well, this turns into 1 minus 1, which is 0, and this turns into a 0. So we'd apply L'Hopital's rule, wouldn't we? It doesn't matter where it came from. All that matters is it is in indeterminate form, and we can apply L'Hopital's rule. So we'll do it repeatedly as many times as you need to until it's not in indeterminate form. Listen carefully. The second it's not in indeterminate form, you can't use L'Hopital's rule anymore. Okay? So unless it's 0 over 0 or infinity over infinity, L'Hopital's rule does not apply. It does right here. So we're going to cite a second use of L'Hopital's rule. We'll take the limit as x approaches 0. The denominator is going to be 6x. The numerator is going to be sine of x. If I wanted to, I could apply L'Hopital's rule, cite that, do it one more time, and yeah, or I could do this. So I could pull the 1/6 out front here and show that that's the limit as x approaches 0, sine of x over x. Limit there ought to be 1/6 because this turns into a 1. I've got the factor of 1/6 or the constant of 1/6 out front. If I wanted to apply L'Hopital's rule again, this is what I'd end up with. I'd end up with cosine on the top and 6 on the bottom. And what happens if I plug in a 1? I get a 1 on the top and a 6 on the bottom. So the right answer either way. Okay? Any questions there? Okay. Go ahead and flip the page over. We're not, I think there's a proof in the book. I'm not sure. If you want one, there are plenty of places on the internet that you can find one. I believe Saul Kahn on Khan Academy has a proof for L'Hopital's rule. If not, there are a couple other good websites. Patrick JMT, I think, has one. But there's some. We're gonna go through a small argument here as to why L'Hopital's rule works the way it does. Okay, so this answer is no mystery right here. If you find it by canceling the factors of x, which you can do because as long as x is not equal to 0, x over x is a 1, right? So the answer on this problem is a 2. If you applied L'Hopital's rule, here's what we'd do. We'd find the limit as x goes to 0 of, I'd have a 2 over a 1, and the answer is still 2. Okay? Well, here's what we're doing. If you think about what the denominator looks like, the denominator is the function y equals x. And the numerator is the function y equals 2x. And what we're doing here by comparing the derivatives is we're basically comparing how big is this function, what's this function value compared to this function value right here, okay? So we're making a comparison about how the two functions approach 0. They both go to 0, but they go to 0 at different rates. This one goes to 0 at a nice steady rate of 1 unit for every 1 unit in y for every 1 unit in x. This one approaches x or 0 twice as fast. It's much steeper, okay? So we're basically comparing how quickly they're approaching 0, okay? And that's kind of the idea. We're comparing the slopes of how they do that, okay? So let's take a look at a couple of examples. These are a little bit more interesting because they're more interesting functions. And they're also not always approaching 0. It's not always going to be 0 over 0. So this is the limit as x goes to infinity of e to the x minus e squared over x minus 2. So this is going to be some gigantic number minus 8. And this is going to be some gigantic number minus 2. So this is infinity over infinity. Cite the fact we're using L'Hopital's rule and apply it. So this is going to be the limit as x approaches infinity. Derivative of the top, e to the x. Derivative of the bottom, 1. Yeah, please don't use the quotient rule. It's going to go really bad really quickly, okay? So what is the limit for e to the x as x goes toward infinity? Infinity, okay? So just as kind of a precursor to what we might see later on, this one goes toward infinity. The denominator goes toward infinity, which normally makes the whole fraction go closer to 0. This one goes toward infinity, which normally makes the whole fraction grow bigger and bigger and bigger. Which one won? The e to the x, the top one won. Does that make sense? Top one grew faster. They were both growing very fast, but the top one was growing faster. Okay? All right, so let's take a look at the next one. So we've got the ln of x over 2 radical x, and we're taking the limit as x approaches infinity. If you wanted to think about what these look like, there's ln of x, and there's square root of x. They're both growing. They're getting bigger and bigger and bigger. Not very fast, okay? But they do go toward infinity for both of them. So we can apply L'Hopital's rule. So we're going to find the limit as x approaches infinity. Derivative of ln x, 1 over x. Derivative of 2 times the square root function. Well, that's going to be 2 times 1 over 2 square root x. Those are going to cancel. I'm going to flip this over to simplify the complex fraction. So this is going to give me 1 over x times square root of x. Is everybody okay with that? So in the simplified form, here's what I've got. I've got the limit as x approaches infinity, 1 over the square root of x. Is everybody okay there? There was a full x on the bottom. There was an x to the 1/2 on the top. I cancel those. I get an x to the 1/2 on the bottom, or a square root of x on the bottom. Is this an indeterminate form anymore? No, it's not, because there's a 1 on the top. There's a 1 on the top, right? Okay, that's what I was just asking. I wanted to make sure. I think of this as x, 1 over x to the first times x to the 1/2. I'm going to cancel this one with that one. If you wanted to do the exponent part of it, you would do x to the 1/2 minus 1. Subtract the bottom exponent from the top. Why bother with a negative exponent when we don't like working with those? So you'd have a square root of x on the top or on the bottom. Okay? You could think of it that way. You could also think of it this way. There's a square root of x on the top, and there are 2 square roots of x on the bottom. Does that work? Cancel. Still have a square root of x on the bottom. Okay, this is tending toward infinity, right? Square root of infinity is still a pretty darn big number, so this is tending toward infinity. So use those ideas that we talked about in Chapter 2. What's the answer? Answer is 0, okay? They were both growing. Which one was growing faster? The bottom was, okay? Logarithms grow very, very slowly, okay? And that argument, that idea is going to come in handy a little bit later. Any questions? Okay, notice this one is very similar to one that we had just a second ago, except for now the point of interest is 2. If I plug in a 2, e to the 2 minus e to the 2, 0 on top. 2 minus 2, 0 on the bottom. So let's apply L'Hopital's rule. E to the x and 1. I still have the limit as x approaches 2. Answer is e squared, isn't it? Okay, stop and think about, if you're any bit of a mathematician, this is kind of cool. Every one of these is in an indeterminate form, 0 over 0 or infinity over infinity, and yet the answers are completely different. Okay? They are totally based on the functions that were approaching 0 or approaching infinity and how they were doing that in comparison with each other. Okay? All right, let's take a look at the next one. Let's see. This is a big number squared minus 2 times a big number. Which of these two is going to control the shape here? The x squared is. It's going to be, a lot of times we'll use the word dominant term, remember that? Okay? And then in the denominator, that's going to approach x squared. So the top's approaching infinity and the bottom's approaching infinity. We'll apply L'Hopital's rule. And we'll get the same thing as if we applied that technique that we learned in chapter 2, where you divide by the highest power in the denominator. Except for we're going to arrive there a little bit, probably in an easier fashion. This is 2x minus 2, and this is 6x. Still going toward infinity and still going toward infinity, right? Apply L'Hopital's rule again. So we'll find the limit as x approaches infinity. This is going to be a 2, this is going to be a 6, and so our answer is 1/3. They were both approaching infinity. Neither one of them won. This is a bit of a compromise. This is a bit of a compromise. Okay? What this says is the bottom one is always 3 times larger in comparison. Its magnitude is 3 times the size of the one on the top. Or if you look at it the other way, the top is about 1/3 the size of the one on the bottom. Okay? For every 1 unit I have on the top, I've got 3 of those same units on the bottom. Okay, as far as size. Make sense? Okay, let's take a look at the next couple. This next one is kind of an interesting example. Is this in indeterminate form? What's the variable? The variable is 8, so if I plug in a 0 here for direct substitution, I get square root of x minus square root of x, so I end up with a 0. I've got a 0 on the bottom, so I can apply L'Hopital's rule. So I'm going to find the limit as h approaches 0 of, well, this is going to be 1 over 2 square root x plus h. Carry out the chain rule. The derivative with respect to h would be 1, dh. You with me there? We're differentiating with respect to the variable in the limit. Good? Okay, what's the derivative of the square root of x with respect to h? It's a constant, so this is 0. Okay? And what's the derivative of h with respect to h? A 1. Now, take the limit as h approaches 0. What do I get? 1 over 2 square root x plus 0, so I just get 1 over 2 square root x. Okay, this is kind of an interesting problem because we just used the derivative of the square root function to prove what the derivative of the square root function is. Kind of an interesting application of L'Hopital's rule. Isn't this the definition of the derivative? Isn't this f of x plus h minus f of x all over h? Okay. So enjoy the irony. Okay, let's take a look at this problem right here. Those darn trig functions do not go away, and they happen to choose a secant here, so that's not the funnest thing on the planet. Okay, stop and think about what that would have to look like. It's related to the cosine, so you'll remember cosine does this, and we do the reciprocal of it. It's got this shape right there. That's one branch of it, and we're only interested in approaching pi halves from the negative side. So what is that limit? Positive infinity. This one's tending toward positive infinity. In order to be indeterminate form, the bottom's got to be infinity. And if we take a look at that, that's tangent of x, which normally looks like this. And then we're just going to add 1 to it. So it's going to just slide the graph up like this. We've still got a vertical asymptote at pi halves. So what's its limit also? No, it's pi halves from the negative side, from the left. Okay, good? Yes, it would. Yes, it would. Okay, but it wouldn't matter in that particular case because all they've got to be is some form of infinity over some form of infinity, either plus or minus. Doesn't matter. You can apply L'Hopital's rule. Okay, so let's apply L'Hopital's rule here and let's see what we get. So I've got the limit as x approaches pi halves from the negative side. I need the derivative of secant, so I just need to rack my brain and figure that one out again. That one was relatively simple. It's not a co-function, so it's not negative. It's secant x, tangent x. And in the denominator, the derivative of 1 is 0, and the derivative of tangent is secant squared x. So I get to cancel a secant here with one of those there. So here's what I'm dealing with. I'm dealing with the tangent over the secant, which I'm going to think of as sine of x over cosine of x over 1 over cosine. Everybody good with that? Why is that useful? Flip that over, so I've got a cosine. I cancel those. So this is the same as finding the limit as x approaches, pi halves from the negative side on sine of x. So we can think about that for just a second. Sine looks like this. Here's pi halves. What does it approach? 1. Approaches 1. Okay? Any questions? Okay. I want to talk for just a second about some very common pitfalls that happen with working with L'Hopital's rule. A lot of times people get a little bit giddy and L'Hopital happy because the rule is so cool and it just works out these awesome limits without much difficulty at all. People will do something like this. They'll say, okay, plug in a 0, plug in a 0, plug in a 0. I've got 0 over 0. I'm going to apply L'Hopital's rule. And then I end up with, this is 9x squared minus 2. And here is negative 10x plus 4. And gosh, this is so easy. I'm going to differentiate again. So this is going to be 18x. And this is going to be a minus 10. And I'm plugging in a 0 and I get a 0. Okay? Got a little carried away, didn't I? Okay? Especially when you're dealing with polynomials, they are so easy to differentiate repeatedly. People will just think, well, I'm just going to keep doing this and the answer is going to drop out. The problem is right here. What happens if you try it? Every time you find the derivative, every time you apply L'Hopital's rule, you have to try and evaluate it by substitution. You're either going to get an answer or you're going to get something that's in indeterminate form. If I plug a 0 in here, what do I get? I get negative 2 over positive 4. So the answer is not 0, it's negative 1/2. That's the correct answer. Don't just blindly start using L'Hopital's rule over and over and over again. Okay? And people will see something like this and they'll say, oh, plug in a 0. Okay, I'm going to apply L'Hopital's rule and I'm going to get 18x squared plus 3x and 10x minus 12 and so forth. What's wrong with that? Okay. All right. Let's say I did differentiate it properly. Did I do that right? Okay. Did I do it right now? Okay. We shouldn't even be talking about differentiating, should we? We shouldn't even be talking about, hey, you made some mistakes when you were differentiating applying L'Hopital's rule. Okay. Should we have even applied L'Hopital's rule? No, because you can plug it in here. You get a negative 4 on the top. That enough right there, trying to do it by direct substitution, there is no way L'Hopital's rule applies here because the top's not 0. Plug it in here, you get a 1. The answer on this one is negative 4. So the lesson here is make sure L'Hopital's rule applies before you use it. Okay? It applied once here, not twice. It didn't apply at all here. Okay? All right, so let's take a look at this one. Numerator is 0. Got that going for us. What is the cosine of pi? Negative 1. So this is 1 minus minus 1. So the denominator is going to be 2. Okay? So the answer to this one is 0. It's not an indeterminate form even at the beginning, but what mistake would somebody make, especially if this problem was in this section? They'd look at this and they'd make some silly mistake and they'd think, oh, it's 1 minus, oh, cosine of pi, that's negative 1. They just write this down, do the subtraction, and get 0 over 0. Okay? So don't have a silly mistake lead you to thinking that you can apply L'Hopital's rule when you can't. Okay? No L'Hopital's rule there. Okay? Okay, so just be careful with those. Okay, any questions? Okay, that is what the majority of your assignment is on. Now we're going to do the hard stuff. Okay, so we've got enough time. We're going to cover this idea, and then I'm going to show you a different way to do this. So in this book, they show a technique for dealing with problems like this. This is an application of L'Hopital's rule. This is in indeterminate form, but it's a different type of indeterminate form. If I plug in an infinity into this factor right here, I get infinity. If I plug an infinity into this, I get pi over something that's getting larger and larger and larger. So this tends towards 0. So the overall quantity gets close to the sign of 0, which is 0. So then the question is the same as we had before. Well, if one is 0 and the other one is infinity, those are competing interests. One wants to increase without bound. The other one wants to squash it down to 0. Which one wins? Okay? This is an indeterminate form, but it's not 0 over 0 or infinity over infinity. Okay? So, here's how this textbook deals with this. Okay? One technique, the technique that this book uses, is divide by the reciprocal of one of these functions. So dividing by the reciprocal of a function is the same as timesing by that same function. So let me show you what I mean here. So we're going to take the limit as x approaches infinity. I'm going to leave the sign of pi over x on the top, and I'm going to divide by the reciprocal of x. Now, this is a perfectly good technique. It works. Sometimes figuring out what function you need to divide by, sometimes that's a pain in the butt. Like maybe you should have divided by 1 over sine of pi over x. Maybe that would be the right technique there. Maybe that would lead you quickly to the right answer. Okay? It wouldn't, but how would you know that without some practice? Okay? So the way we do this is, look at this. That tends towards 0, right? This tends toward 1 over infinity. 1 over something that's getting closer and closer to infinity is 0. Okay? This is now in an indeterminate form. It has to be a quotient. L'Hopital's rule only works on ratios, the ratio of that top function over the bottom function, and it's got to be 0 over 0 or infinity over infinity. We now have it in that format, so now I can apply L'Hopital's rule. So let's do L'Hopital's rule. So it's still going to be the limit as x goes to infinity. This is going to be the cosine of pi over x times the derivative of pi over x. The derivative of pi over x is negative pi over x squared. Correct me if I'm wrong. Let's just do a little work off to the side here. That would be pi times x to the negative 1. That would be negative 1, pi, and then x to the negative 2. Isn't that right? So wouldn't that be negative pi over x squared? Yeah.
So that sine of x, where's that bringing that? Is that negative?
What?
What's that slash?
It's a dot over the I. Can't you tell that?
I thought that was
a sine inverse or something?
Yes.
No. Why would I do that? Why would I make a silly mistake like that? No. Thank you for pointing that out. Okay. We on track here?
So you can just divide by
That dividing by 1 over x is the same as timesing by x. Can I just flip that over?
Okay, yeah.
It's just an algebraic technique. We normally wouldn't do that. We're making a complex fraction. We normally don't like that.
Yeah.
Okay? So I find the derivative of the top. Now let's find the derivative of the bottom. Derivative of the bottom is negative 1 over x squared. Isn't it? Okay, same reason here. Just pull the pi out of there. Right? Why is this helpful? Because now I am going to use a complex fraction in the way that I typically do. I'm going to multiply by the reciprocal here, yes?
For the negative pi x squared, we're not just negative 1.
With negative 1x squared? No, because the pi is a constant. Think for a while. That's right, isn't it? Everybody see that?
Yeah.
Okay. So why is this helpful? Now I'm going to take this and I'm going to simplify the complex fraction. So this is going to be multiplying by negative x squared over 1. I take the denominator, flip it over, and multiply. Why do we like this? Because then I can cancel this with this. I can cancel the negative with the negative. So I've got this. This is the limit as x approaches infinity of, I've got a pi sitting out front, and I've got the cosine of pi over x here. Now, there is no way this is in indeterminate form. We're going to be able to get the answer here. This is a pi, plain old constant. And what happens when we plug in a larger and larger number here? That gets close to 0. And what does the cosine of 0 approach? 1. So what's the answer on this one? The answer on this one is pi. Okay? Now, we're good? Nope. Nope. That was the advantage. That's the nice thing about finding the derivative. Okay? Okay, now, I'll tell you this. I am not a huge fan of this technique. When we come back tomorrow, I'm going to show you this technique right here. I like that a little bit better, and it has to do with what we did in the starter question right here. Trading behavior 0 for behavior at infinity. Okay, it accomplishes the same thing, but in my opinion, it's a little easier to understand, and a lot of times it's much quicker. Okay, all right.